So you'll remember that when we talk about classical probability, what we're trying to do is count the number of outcomes in the event and count the number of events in the sample space. Now, for some things, this is very easy. If we're trying to roll a single dice or toss a single fair coin, it's very easy to count how many possible outcomes there are. There are 6 outcomes on a dice, 2 outcomes on a coin. It's a bit more difficult if we have a number of processes, or if we repeat the same process a number of times. For example, if we roll 3 dice or toss 10 coins, or maybe if we do a mixture of different processes, then it can be a bit more difficult to count the number of outcomes. There's one key thing that helps us here, which I'm going to call the multiplication principle. And the multiplication principle is this. If I have n choices, and then I have m choices, then altogether I've had n times m choices. So if I have 5 choices of one thing and then 7 choices of another, then altogether I have 5 times 7 choices, or 35, the number of pairs of things. An example I use in the notes is pretend you're going to a burger restaurant and there are 3 choices of burger. You can have perhaps the beef burger, the chicken burger, or the veggie burger. And there are 2 choices of side. You can have the fries or the salad. So that's 3 choices of burger, 2 choices of side. And overall, you get 3 times 2 equals 6 choices. Right, there's the burger with beef burger with fries choice, the chicken burger with fries choice, the veggie burger with fries choice, beef burger with salad, chicken burger with salad, veggie burger with salad. So that's 3 times 2 equals 6 choices altogether, because you've got like 3 choices for the column, 2 choices for the row, and so that gives you a 3 by 2 rectangle. So that's this multiplication principle. And it works for more than 2 choices, right? If I have n1 choices followed by n2 choices followed by n3 choices, then overall I have n1 times n2 times n3 choices. So maybe we should just write that down before we go further. So the multiplication principle is that if we have n1 choices, then n2 choices, etc., all the way to nm choices at the nth stage, then overall we have n1 times n2 times n3 times nm choices. And this will be useful for a number of things. Let's start with a simple example, which is this. We toss 5 coins, 5 fair coins. What's the probability that they're all the same? So that they're all heads or they're all tails. What's the probability that that happens? So here, the sample space omega is the set of all sequences of 5 heads or tails. By that I mean, it could be head, 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 head. It could be head, 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 tails. It could be head, 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 tails, head, 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 tails, tails, etc. So, how many elements are there in omega? That's what we need to know. Well, there are 2 choices for the first coin, all right, which could be heads or tails. There's 2 choices for the second coin, which could be heads or tails. 2 choices for the third, 2 choices for the fourth, and 2 choices for the fifth coin that could be heads or tails. And so by the multiplication principle, right, we multiply those together. Right, it's 2 for the first coin, second coin, third coin, fourth coin, fifth coin, or 2 to the 5, which is 32. So there we've used the multiplication principle to remind ourselves that 5 choices of 2 things is 2 to the 5 equals 32 in total. What about this event A, that all the coins are the same? How many possibilities are there? Well, one possibility is that they're all heads, head, 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 and one possibility is that they're all tails, tail. Those are the only ways that all 5 coins can have the same outcome. So it's clear from that that the number of elements in A is 2, right? We can just see there are 2 outcomes in A, the all heads outcome and the all tails outcome. And so the probability of A is the classical probability, number of elements in A over number of elements in omega. We said there were 2 elements in A, 32 elements in omega. It cancels out to 1/16 if you prefer, which is about 6%. So there's about a 6% chance that all 5 of your coins come out with the same result. Let's do a very slightly trickier example, which is that we roll 5 dice. What's the probability we get at least 1/6? Well, again, we need to know the number of elements in our sample space and the number of elements in our event. So omega, here is the set of all sequences of 5 dice rolls. So again, there are 6 possibilities for the first dice, 1, 2, 3, 4, 5, 6. 6 possibilities for the second dice, for the third, for the fourth, and the fifth. So it's clear that that's 6 to the 5, right? For the same reason, by our multiplication principle, we multiply together the choices on each of the 5 dices to get 6 to the 5. And I put that into my calculator earlier. Apparently that's 7,776. Now, the event A that we roll at least 1/6. I have a little tip for you here, which turns out very useful, which is that this is an at least 1 question. And you quite often come across these at least 1 questions. And my tip is, whenever you see an at least 1 question, try and look at the complementary event instead. So because we've got an at least 1 question, instead look at A complement, the probability that A doesn't happen. Because if it's not the case that we get at least 1/6, that means we don't get any 6s, right? And it's normally the case that with these at least 1 questions that the complementary event, that you get none, is easier to count. So there's a little tip that might help you out on problem sheets later. If you see an at least 1 question, look for the complementary event. So what's the number of elements in A complement? Well, for the first dice, it can be 1, 2, 3, or 5. 1, 2, 3, 4, or 5, but it can't be 6. Right, so we've got 5 choices for the first dice. And similarly for the second dice, it can be 1, 2, 3, or 5, but it can't 3, 4, or 5, but it can't be 6. 5 choices. So in fact now, if we're going to avoid getting any 6s, we've only got 5 choices for each of our 5 dice. So this now is 5 to the 5, because there are 5 dice and we've got 5 choices for each of them. And I didn't calculate this earlier, some big number. But the key is now that if we want to find the probability of A, we know that that's 1 minus the probability of not A. The probability of A happening is 1 minus the probability it doesn't, or the other way around. The probability that A doesn't happen is 1 minus the probability it does. We proved that in the last section, or in fact you proved it on the problem sheet. And so this is 1 minus, and then the classical probability here is the number of elements in A complement over the number of elements in the whole of omega. That's 1 minus 5 to the 5 over 6 to the 6. I did calculate that earlier. That's 4651 over 7776, which it turns out is about 70%. So there's roughly a 70% chance you get at least 1/6. But we calculated that by finding out that there was a roughly 30% chance of not getting any 6s. So when you have an at least 1 question, try and look at the complementary event. And then it can be easier to use your multiplication principle. When you have multiple choices, the total number of choices is the multiplication of all the individual choices.